The other thing about my background is I was actually here on my first sabbatical. So it was a while ago. It's 19 years ago. So it's right back there and that. Salah and Hugh were my hosts, and so it's great to see the Rose Building again. I'm not sure if there was AC at the time, correctly. Okay, so I'm just going to talk a little bit about because I know some of the work that has done here when our student Katie was here was about data sets and data collection. So I want to talk a little bit about some of our data sets that we have been focusing on, but then some of the research that follows up. So I want to acknowledge I have a couple of collaborators, especially at the top here, Killian Weinberger, who is Katie's advisor in computer science, Brad Harry-Haran, and Harry Chow, who's at Ohio State, used to be a postdoc for us. So those are all faculty members, and everybody else, the students, do most of the work. So we'll talk a little bit about that. So what we've been focusing on, my group has been involved in self-driving cars since the 2007 DARPA challenge. And so we were one of the cars that was part of that challenge. We were able to finish the challenge, and it really sort of spawned us to look at a number of different research aspects like that. I would say more recently, we're particularly interested in a couple of different challenges, I would say. The first one is poor weather. So I'm going to show here a video on the left. So this is Cornell. It's probably what it looks like right now. To be honest, when I left, it was minus 15 degrees centigrade. So it was quite cold, and unfortunately, I got to go back there tomorrow. But this was a data set that we collected. I'm going to talk a little bit about this, but this is the interesting aspect of it. You'll be able to see this here. We're sitting here at an intersection. There's traffic light. You see all the students are basically meandering, going to class and things like that. But then a car gets stuck. So then people sort of come out and start pushing on the car for a little while. So this kind of data set is kind of a gold mine. So for a while, we were just sort of driving the same route, and every once in a while, things like this would come up. We'd have fog or other kinds of anomalies that we'd be looking at. So it's particularly interesting to look at in terms of different anomalies as things go on, right? So I'll talk a little bit about this as we go along. So the second challenge is that for the past 5 or 6 years, I've been to Hanoi, Vietnam several times. And the second to last trip there, we actually did a data collection. And so this is not part of the data collection, but it was something that sort of motivated us to be able to do that. So I don't know if you've been to Vietnam. I think if you go to Naples with the scooters and other places like that, places in China and India and things like that, it's just really kind of hectic. And so looking at tracking and forecasting and autonomous driving in those kinds of environments where the structure is very, very different. So this is an intersection here, and you see everybody sort of just going in different kinds of directions. So you can think that self-driving cars and those kinds of areas are particularly challenging. So I'll show these videos a little bit later, a little bit more full. So those are the kind of things that we're particularly interested in. My group is interested with Killian, Brad, and Harry. So what I'm going to talk about today, I want to talk about the data set that we collected. We called it Ithaca 365, and I'll talk a little bit about what that means. It's particularly good for weather conditions, but also repeated routes. And then I'm going to talk a little bit about some of the research that we did using that data set because of the uniqueness of the data set. And I think it's important. I know there's we're waiting on the CVPR paper to see if there's if that data set can be published and things like that. But I think it's important to build on it and show how that can actually be used in the community. And I'm going to talk a little bit about the Hanoi data set that we collected as well. All right, so I'll first talk about Ithaca 365. So what we have here, this is just a map of Ithaca, okay? And so Cornell campus is right up in here, and you see the red line in here is about a 15-kilometer route, okay? And so this actually occurred during COVID, is we drove this route multiple times. We ended up driving it about 150 times. And so the students would just come down, turn on all the sensors, and drive the same. And on that, we had high precision GPS, including some corrections using an antenna on top of our building. We had 100 Auster LiDARs, 128 scan LiDAR, 4 different cameras, and we do a little bit of labeling, which I'll talk about. This is our second car. We had the first car for the challenge in 2007. This is our second car as we have one on. The interesting part about this is there's a pictures there on the right-hand side, is that we can dial into anywhere on this map, and I can show you 40 images of the same location, but over different weather, lighting conditions, and those types of things. So that's the interesting part about it, the fact that you have repeated traversals, but also you can look at it in terms of weather conditions, lighting conditions, and those environmental conditions as we go on. So the pictures on the right are 6 different scenes of the same exact location. Okay. So what we did with this is that we were particularly interested in time amodal data, which is looking at data such that every pixel or different pixels would have multiple labels. Okay. So the idea here is that if I look at this, is I have a car here, but I have a car behind it as well. Down here, I have a car, but underneath I have a road. And so when we did our labeling of time in the segmentation, here's a person and behind it is a truck. We did the segmentation, but we also overlapped these so we could actually look at some of the called amodal data. So I think that's been used in the community. Okay. So that's one a unique aspect of what we're doing. So in our data set, of course, we have 3D object labels, which are kind of shown on the left-hand side of this. We have the amodal instant labels, which I was just talking about, which is on the right-hand side of here. And we so that we have it in with the LiDAR data and the camera, the 4 different camera data. The other thing we have is we actually have road information. And I thought the road information was going to be particularly interesting, particularly because let's say you have certainly if you're in a bigger city and you lose GPS or you don't have as much map information. But the other aspect of it is that you have snow-covered roads. That first video that I showed you, you can't really kind of see what the road is at the time. And so that's one aspect we're particularly interested in looking at. Okay. So yeah, so you can see a little bit of this. And because we were driving this route multiple times with high precision GPS, what we could do then is we could take our road labels on the nice sunny weather and transform them and move them on into and be able to label sort of snowy conditions. So in summary, what this is in terms of our data set, 15-kilometer routes. What we published, we have more than this, but we published 40 traversals, about 17K frames per traversals. That includes the LiDAR and the imaging. And we annotated just about 7,000 frames, so not as much as we had hoped. Annotation, as you know, takes a lot of time and funding. Okay, so I'm going to talk a little bit about now a little bit of some research that we've done building on this. So that was published in 2022, so about two and a half years ago. So one aspect that we looked at was because we have images of the same location under different kind of conditions, is we could then try to look at translating those from, let's say, snowy conditions to night conditions. And that's what we've done right in here. So, and then what we looked at is okay, well, instead of doing detection and looking for roads on the left-hand side, what happens if you can actually do it on the right-hand side? So this is from 2023, so a little bit later. So on the left-hand side are the snowy images, on the right-hand side are the sunny images. So it's you can sort of see the differences primarily in the green of the trees and those types of things, right? But when it gets to be snowy conditions, it's really where it actually particularly helps. When it's not snowy, there's not much of a major impact. So that was one aspect that we were able to do it. It was just image translation, and that was published in 2023. There's some other work. This is work that I think if Katie presented here, one of Killian's students when she was here last spring, she probably talked a little bit about that. We called it hindsight, which is basically using the repeated traversals. Our thought process with this is that many times if you're driving, you drive the same route all the time. And so can you take advantage of that information going along with that? And so the idea of this is that you just take all the LiDAR inputs, and as you're driving, you get better and better at understanding what the scene is and what the differences are. And so basically, this work looked at, it uses the past traversals, but it basically used no labeling or anything like that. It's basically you just kind of learn from driving it in multiple traversals. So this was a series of papers that were led by some Killian Weinberger students as we go along. And then in terms of the amodal data, where we were particularly interested in shape completion, so that there was a partial detection of a person or a car or something like that, using the amodal data, hopefully be able to put it through some type of pipeline and be able to figure out where the entire car was as we go along. Okay, and so that's a little bit of some extra work we've done. So this was in 2020. But what I'm going to spend the majority of this talking about is visual localization. Okay, and really looking at uncertainties in deep learning. So my group, we work a lot on perception, and we collaborate with Killian and Barat on deep learning. So my group only does a little bit of deep learning, a little bit on the planning side, but for the most part, we're on the perception side of things. Okay, and I'm going to talk about visual localization here, but our original goal was to understand errors that deep learning makes, and we use visual localization as a vehicle, no pun intended, to help us with that. And that's and the reason that we did that is because we had these repeated traversals. So I'll show you how we actually use that. So this is our visual localization pipeline. So again, some of the details here don't matter as much, but I'll explain a little bit what it is. So I think a lot of people probably know what visual localization is, but basically these are the different data sets. So think of this as this is data set 1 all the way down to n. This is the 15-kilometer route that I've talked about, right? So if I have 9 of these are, this has an image and then an XY GPS tagged pair. Okay, and I have that, let's say, for 17,000. I think in this case it's 15,000 images because we threw some things out to kind of balance the scenes as they're going. So this is the database that you have. Okay, and so then what we're doing is we're doing a feature-based approach in terms of deep learning. There was 2 steps to this, primarily from a computational standpoint. This was a global feature matching to figure out which of these images best match the query image, which I'll talk about in just a minute. And then once we get, let's say, a top 10, then we did a finer grained approach to that. So I talked a little bit about some of the approaches that we used, but the point of this talk is not really, oh, is it the best visual localization approach or some of that. The point of this is that we want to figure out what mistakes it makes and can we predict those mistakes. That's really the focus. So the case study that we're doing here is the following. So we basically had 9 prior traversals, and typically what we do is we get sort of 3 sunny, 3 snowy, and 3 rainy, 3 night. Okay, so that's typically because we wanted to balance the 3 different data sets. So this is basically the traversals that we had previously, and then this is our query image. So think of this as now I'm driving right along here. We're driving along, and I want to take that image, which is right in here, and I want to say, okay, which image in my database is the closest one? So I do my feature matching as I go along, and then I pull out the position. Okay, so that's the visual localization. Okay, and we want to figure out is, okay, what do those errors look like? So the first thing I'm going to show you is I'm going to show you basically just a, if we did this for the query image, okay, here, and we did it for one full 15-kilometer route, and then I repeated that for a sunny night and snowy conditions, you get something, and looked at the errors, you get something that looks like this. Okay, so this is the car forward direction, this is the car lateral direction. So if you're driving in sunny conditions, you look at this, and it actually looks semi-Gaussian if you sort of squint at it. Okay, it actually does a pretty good job. Okay. If you look at snowy conditions all the way on the right, it's a little bit more. It doesn't. It's not quite Gaussian, but it's a little bit closer. You see a few more outliers as you go along and things like that, right? The key is at night you see these tracks that sort of go all the way out, so it just gets locked onto something, and errors just continue to grow as it goes that long. So this is distinctly non-Gaussian, and it kind of makes sense because you're at night and you're using features, and those are driven by visual features and things like that. Okay. So the night is the worst condition, which surprises us a little bit. We thought the snowy conditions, especially in really snowy conditions, like I showed at the very beginning in that video, would be the big part of that, but it didn't really kind of drive that. Okay. So the first thing I'm going to talk a little bit about, and so I'm going to analyze some of these, and then talk about how we would try to estimate the covariance. That's kind of where. So the first is let's kind of analyze this and see what it is. Okay. So these are the features. So remember, we're taking an image and we're trying to figure out features to match each of those. And the number of features changes depending on the scene and depends on lighting and those types of things, right? So this is the error, okay? This is just a post-processing. This is an error as a function of the number of key point matches in the image, okay? So if I come back here, it's basically these matches as we go along. That's what that horizontal axis is. So if I take a look at this right here, you see, I have a few in here that have, 2 to 400 and things like that, but a majority as it comes out in here, not a majority, but it's basically kind of spread as we go along here. But for the most part, this is in meters. It's, sort of under 4 meters, which is actually pretty good. Again, if I go to the snowy, there's a little bit more, it's a little bit higher, up to about maybe five meters and things like that. You see this sort of tails off down in here. I get a fewer down in here and a little bit more up in here. But again, for the night query, I have a lot of images that have between 0 and 200 feature points, whereas I don't have hardly any in here, just a couple, and then a few more in here and things like that. Okay, so just it'd be nice to use the number of features as a proxy, but it doesn't necessarily work out that way. Okay, so you have a lot of more distributed errors and things like that. So you can't just continually add more data sets. You've got to be hopefully be a little bit more smarter in terms of how you're doing that. So then we looked at some of the outlier errors, and I'll give you an example of a couple of them. So the first ones are in terms of some night conditions. Basically, if you had lights that were far away, okay, it would lock on to a number of those lights. Okay, and that's really where a lot of the big errors would actually come with night conditions and things like that. But we had a lot of outliers in daytime as well. Not a lot, but we had a few. One of which would surprise us, is we have some basically cobblestone roads. There's one long cobblestone road that we were driving on. It's about 1.5 kilometers long. And you see all these features that actually get mapped. So that's very, very high features, but the road looks very, very similar. So it has to use some of the other context it's seen to be able to figure out actually what's going on. Some of our outlier errors are because of that. So again, just looking at the number of features isn't necessarily exactly what it actually wants. Okay. So what my group has been particularly interested in doing is, if I can explain in this, is that most deep learning, what you do is you take that query image queue, you put it in the deep learning algorithm that I showed, and then you get out a prediction. Okay, and then you use that prediction inside of the estimation. Okay. But what we're particularly interested in doing is I don't want just the z hat, I want a likelihood. Okay, and that likelihood gives some evaluation of that uncertainty, which then I can use inside of the perception block. That's what I would like, because my group lives in the blue block, which is the perception estimation block, as opposed to deep learning as we go along. Okay, so this is what we're particularly interested in. How do we figure this out such that I'm not just getting a prediction, but I'm also getting a likelihood function? Okay, so I'm going to show some plots. So I'm going to give two different methods. One is just constant covariance from the data sets, and then the other one sort of adapts. And we've had a couple of follow-ons since then. We're going to get some Gaussian mixtures, but I'm really just going to talk about those two right now. But I want to show you sort of an analysis tool that allows us to kind of look at that. So because I'm going to show some different plots of this. So the first is, this is very similar if you've studied hypothesis testing inside of common filtering and things like that. It's very much aligned with those kinds of things. And so if I'm looking at this is Z ground truth. So this is using our high precision GPS. It's actually what comes from our prediction and things like that. And then we have some type of covariance that goes with that. Okay, and that's what we really focus on, is that covariance. So this is a chi-square variable. And so in essence, I'm going to look at the tails, the low tail and the high tail. Okay, and the high tail typically, not always, but typically is because the prediction errors are quite large. And the low tail typically is because the covariance is large. Again, not always, because again, if I get a great prediction in here, this is 0 and I'm going to get something in there. But on average, okay, it shouldn't all be down there. So I'm going to kind of show that. Okay, so that's a little bit of a metric that I'm going to use. But then I'm going to do something kind of weird here, is I'm going to put it on its side and look at the log plot, just because it actually makes a little bit more sense. So this is the same metric that I showed before. So again, the lower part here means that I have a larger covariance, and the higher part here are the outliers. And then this right here, this is my test statistic. So this is the lambda that I'm looking at in here, but it's a log scale. So basically, anything from here, this is about 0.5 down. So this line right in here is right in here. So everything down in here is just this little orange area. Okay, so it looks a little bit bigger, but only because I wanted to see what was actually happening at the low side of it. Okay, so these at the top are the bigger errors, and then everything in between here is kind of where you want to live. This is where 90% of the errors should actually live. Okay, so all these plots are going to look at this, and then this is basically measurements over time. So you want to think of this as the 15-kilometer drive. So I start out on campus here, I drive downtown, I drive out on the highway, I come back to sort of suburbia, and then I come back to campus. So that's what's happening along in here. So I'm going to explain that a little bit as well as we go along. Okay, so again, these outliers down in here are typically due to, you know, a few small errors, but a lot of times it may be, if I have too many down here, it's because I have a big covariance. The outliers up here are because I have just big outlier errors. My Z prediction is incorrect. Okay, so, and these are at 5% thresholds. We could have, in fact, we looked at a different thresholds as we go along, but so this is 5.8% instead of 5%, so pretty good. This is 6.3%. So this is for the sunny conditions. So again, for the sunny conditions, if you're looking at a constant covariance, it actually works pretty well. Okay, so if I come back over here to sunny, see what happens is that I get 17% outliers here and about 3% in here. Okay, so it's a little bit incorrect in that case. Okay, but the incorrect are outliers. So basically, there's a few more errors in terms of my prediction Z. Okay, but the more interesting one I think is the night conditions. The night condition, as I come along, the first half of this almost is actually pretty good, and then it basically is just completely out of whack. It goes high and it comes back down and things like that. So it just goes completely out of whack. So you can see this is about 4.7%, but then I got 30% in terms of the outliers. So then the question is, why is that happening? Okay. So much bigger errors in that area. So what's actually happening there? Well, this is actually basically highway driving. And so I thought I had a map on this, but I forgot I didn't put it on here. So the idea here is that there's big, you know, from here to here, we're driving along a 4-lane highway, okay, on the right-hand side. And for the most part, it looks exactly like this until you come up and there's actually a sign. So as you're driving along there, it almost all looks the same, especially for about a half a kilometer of that. So it looks exactly the same. So this is why it sort of flips back and forth and things like that. So you get a lot of errors that are going on there. It's especially worse at nighttime as we go along. So again, there's a sign there that kind of locks it on. Once we get close to the sign, it's actually not as bad. Okay, so there's not too many, what's happening in here, when you're driving on that highway, there's not too many key points, and it all looks kind of the same. So a second solution is we were looking at a data-driven covariance, okay? And so what we wanted to do then is we wanted to take our data sets here, okay? And then we wanted to basically look at those key point maps that I showed. So this is the error, this is the number of key point matches. So it's basically those plots that I showed a little bit earlier. And I have 9 of these because I have 9 databases. So I have 9 of these errors. And I'm going to just put them all in this, and then I'm going to bin them into different bins. So now when I have my query, I'm going to figure out, okay, well, how many key points do I have? Which bin am I in? And then once I know which bin I'm in, I'm going to analyze all of these cases in here to figure out what the covariance is. So I estimate the covariance, I estimate my confidence in that covariance as I go along. Okay. So basically, every time I do a query image, I'm going into those bins. Okay, try to figure out what that is. Okay. So the good part about this is that it's actually using prior traversals and all the data, not just the bin data, but the errors to figure out what the covariance is. But not so good is it's really driven by data. So you got to drive it 9 times to really understand this thing. So let's take a look at what happens with this. So again, this is the same plot that we had before. This is the same test statistic and things like that. What's happening in here is that if you remember, this was, you know, I think 6% and 5% roughly. Now it's 2.5 and 11. So this is kind of all shifted down a little bit. Okay, so the covariance is maybe a little bit larger than it was in the constant covariance case. But at night, you see what happens is that once I get down into here, it shoves it way, way down. So in essence, what's happening in this, when you're out on that highway and it's night conditions, is I create a really, really large covariance. Okay, because I have very few key points, and I know from past traversals that my errors are actually huge in that case. Okay, so effectively what it is I'm getting a lot of cases down in here, and then I get a covariance based on that first bin. And that's going to be very, very high. So it relies really on the past traversals at night. Okay. So in essence, it's better, but the covariance is large and it's almost too large, but it's probably better than it was, you know, previously. So let me relate this now to the map information so you can actually see. I probably should have shown this a little bit earlier. So this is our map. As we're going along, I think this is rotated. So we're starting in here. This is driving downtown. This is where the cobblestones and the bricks are as we go along. This is just sort of suburbia. And then we get on the highway right in here. So this is the area right in here, and we subsample this. this is that I showed where it typically makes mistakes. And so if I look at this as sort of the three different conditions, it's the error and the covariance. And I know you can't see these numbers, but let me, I think I highlight them. So basically, again, this is adaptive covariance. So every time I do a query image, I'm calculating a new R hat, a new covariance. And so during sunny conditions, out in this area, it's high, but the sigma is just 1.2 meters. Okay. And then at snowy conditions, it's a little bit larger, about 1.8. But at night conditions, basically up to 8. So when I'm downtown, this is all green in terms of, down here into the tens of meters and things like that. Up here, or right down in here, it's really, really large. So bottom line is it's doing something. It's in the right trajectory of doing something good, but maybe not necessarily perfect in terms of how it's doing it. It's almost overcorrecting that way. So this is just an analysis of trying to find an error covariance of the sensor itself. And so, of course, what you can do then is plug it into a common filter. And so if you've studied these, and I think most people here at ACFR probably have, now what we're going to do is we're going to plug it into this and use a measurement likelihood using that covariance as we go along. So we do the prediction update like we typically do as we go along. And so we compare it then to the constant error covariance. So I have some numbers here just to show you. I don't want too much time on. But basically, there's two methods we're comparing. One is the constant covariance that I've shown, and the other one is the adaptive one as we go along. Okay. 3 data sets. There's sunny, night, and snowy. And then in orange here, these are the errors in the data set. So this is the error if I go around. If you remember the sort of the scatter plot that I showed at the very beginning, the average error was 0.87 meters. The average error at night was 8.7. The average error at snowy is 1.42 meters, things like that. But I think the more interesting thing is going to be the covariance as we go along, which I'll talk a little bit about that. Okay, so now we plug all that into the filter. We did not use an IMU in here. Okay, and the reason we just basically used a constant velocity model. And so if you really want to do, if your goal is to develop the best visual localization estimator, use an IMU, right? But that wasn't our goal. Our goal was to figure out, okay, if you just, we were really relying on the likelihood part of it, and we wanted to figure out how important that was, because it'd be very easy to just kind of throw out, easier anyway, so throw out some of the errors associated with using the IMU once you get locked on, okay? So I think the interesting part here, these are the average errors, okay? So they drop a little bit in here. This goes from 8 to 3. Again, sort of the more interesting part is what's happening at the nighttime and things like that. And then we looked at the traditional 1 sigma, 2 sigma, 3 sigma. So even though this is kind of non-Gaussian, we wanted to look to those just to kind of compare those as we went along, okay? And so ideally it looks something like this, but it ends up being, and you can sort of see what happens is that certainly it's pretty good in terms of the adaptive case, things like that. If I look at the nighttime conditions, which is the more interesting one, I had 38, 67, and 78. So that basically is not very good in terms of trying to match what's actually happening in terms of the output of deep learning approaches, things like that. And it's much better here, but it's still not quite, in terms of, picking up the outliers as we go along. Okay. So this is a video showing one of the harder conditions. So it's snowy conditions on the highway as we go along. So I'll show someone like this. The interesting thing, let me sort of point this out. The blue ellipse is from the common filter, and the orange or yellow measurement is right in there. So ideally, they're sort of right on top of one another. And so the first thing I want you to see is that this is the adaptive approach. It has a much bigger error covariance, okay, coming actually from the filter compared to this measurement as we go along. And so this is just a video that goes along. And the main thing I want to see here is that this error covariance of the common filter is too small. And basically, if you had, let's say, hypothesis testing, you would be rejecting every single one of these kind of things, right? So I think in this case, we didn't actually reject it. And once the sign comes along, then it's sort of inside, okay? So we can kind of figure out as it goes along, the same thing in here, if that error covariance shrinks as it's going along, okay? So the common filter in the adaptive approach has a much bigger covariance, okay? So it's more consistent, but it has a bigger error. Okay, whereas the baseline is overconfident. And then we also tested it. This is in a paper from a couple years ago. I think it was Ithaca, if I remember correctly, where we actually corrupted the images and actually did a really nice job of that. Okay. So if you add some of these other things, like you would typically do in a localization filter, in IMU, formal hypothesis testing, things like that, it works a little bit better. We've added in since then. We've looked at Gaussian mixture models as an add-on. We started to look at semantics to add in, give more context to actually what's happening in here. So I think there's some interesting things looking in here, but again, our goal for the most part is not to say the best visualization, but it's really more interesting to look at the errors of that. Okay, final slide I want to talk about, the final couple slides I want to talk about is this Hanoi dataset. So as I mentioned, I traveled 5 times to Hanoi for about 5 or 6 years. And in October 2022, I actually took a couple of cameras. I took 2 16 scan LiDAR and GPS, not hyperprecision, but just regular GPS. And we mounted it on top of one of their cars, and we did a couple of data collections. And so I'm going to show you a little bit about what this looks like. So this is actually from one of the cameras of the car. And the interesting aspect of this is, of course, there's many scooters, as you can kind of see as it goes along. But the thing is, there's a handful of traffic lights, but there's a lot of intersections that there's no traffic lights. It's basically kind of, I don't quite know, but they know the rules of the road, right? So, so it's very interesting. So, like, if you're going to do a left-hand turn, so again, this is on the right-hand side, and you're going to do a left-hand turn, you never stop. Like the first time I was in Vietnam, I had a colleague there who grew up in Hanoi, and she said, "I'm going to hold your hand and we'll go across the street," right? Because you can't stop. If you stop, that's not the behavior they're looking for, right? You need to keep moving, but you have to just do it slow as you go along. So that's what happens. So if you want to turn left right in here, you don't stop. You just kind of go here, and eventually the sea parts around you as you go along. So there are local behaviors. I think from a learning perspective, especially with the scooters, it'd be really pretty cool as we go along. And it's very challenging as we go along. So now what I'm going to do is I'm going to show some. So what we did is we actually just ran some semantic segmentation on this data just to show how well sort of the current state of the art works. And so there's a few successes. So this is the same video, but I'm going to show you a couple of different examples. So there's a couple in here. There's that one, and that one. So if I run this, even as this one goes in front of that, I'm still detecting the same object as I'm going along. And so it actually does a pretty good job as one. So there's some successes like that that are actually pretty good, but then there's some failures as well. So this one, again, I have 3. I have this one, and this one. So these are a little bit different. And once this one passes here, basically they go away. Okay, and so the occlusions, if you get, it's definitely correlated with range, okay, but not always with range. It's partially with range and things like that, and those detections go away. So if you have a tracker on that, well, that will certainly help you because you're working on that. But then once you have so many objects, so you're going to be tracking 50 scooters, or you're just going to be tracking what's close to you, right? So this is kind of a challenge that we're particularly interested in looking at as we go along. We have this data set, but much what we had talked about, I think, earlier today, labeling this data set is particularly challenging. So many objects in the scene. And the interesting part about this is learning the behaviors. And that means you need a lot of data labeled for that. And so we've auto-labeled some of this to kind of look at that, but there's challenges associated with that. Okay, so final slide. Let me go back and to these videos and talk a little about some of these continuing challenges. And so, okay, so there's different challenges that go along with this. So again, it's hard to see where the road is. You have a lot of snow coming down. Here you have cars that are just doing U-turns right in the middle of the road. So behaviors typically, at least in Ithaca, typically don't happen too much as we're going along. There's a lot of pedestrians on the side. There's interesting questions here. Do you have to track all these people? This is one of the more interesting parts of the scene. You see people sort of walking across the street here. So our car is stopped here and waiting for them. But as they're coming across, basically a lot of students just sort of stop right in the middle of the road and get on their phone and start texting, and they're stopped right there. And so we couldn't so we weren't driving this autonomously, by the way, hand driven, by my student Carlos. And so you might ask, okay, do all Cornell students are on their phone in the middle of snowstorms? The answer is no. They all got a text this time saying classes were canceled. So they're just trying to figure out whether they're going back to the dorms or not. I think
that's the reason they're working backwards.
What's that?
That's the reason why we're working back now.
Yeah, exactly. So I think that's that. It's so this is one of our data sets that we actually had. So I think there's some interesting aspects here, looking at the road location and slip that goes along with that, and things like that. But even the driving behaviors are different, right? Not just like pushing a car and things like that, but people drive more slowly in this kind of environment. So the forecasting would also be different, weather conditions. Like that. So now there's starting to be more data sets with different kinds of weather conditions. I think there was one that came from Canada at the time we published this data set, but this is one of the first ones that. And then of course the second thing is the Hanoi data set. So again, this is not the Hanoi data set, but I typically give this to talks because I think there's some interesting behaviors associated with this. So there's of course many scooters as go along. There's people crossing in front, depending on what's actually happening. But then when you get to this intersection, if you look at this intersection again, there's that way and this way, and then you're going to see some people trying to cross the road. They're heading in this direction. I don't know what it is. Right? These people are just, again, they never stop. They're just everybody goes around them, right? So there are some behaviors here. I don't quite know what it is. It's just phenomenal, right? My eyes were closed when I was talking this. But I think this is more interesting when they're just selling balloons right in the middle of the intersection. That's pretty cool. So that's tough to predict in terms. Okay, so I think those kind of data sets and challenges associated with those kinds of conditions where you have very dense conditions, many objects, where you're not going to be doing tracking and forecasting with every single object. You're going to be more interested in things that are close to you. Those are some interesting challenges that go on in terms of outliers. There's a lot of inclusions and objects and things like that. So because there are definitely learned behaviors in that. Everybody knew how to drive in that environment. And so I think it's an interesting aspect of it. So that's it. Thanks.
I think we got a question online. Let's see.
Professor Campbell, can you hear me?
Yes.
Excellent presentation. I'm very intrigued by the Hanoi video because I think it's something that's very much not addressed in a lot of autonomous driving scenarios. What about the communication between a car driver and scooter drivers or pedestrians when they look at each other to see what their intent is? This I find is a problem that I don't know how they're going to be a solution for the autonomous vehicle to implement that communication with arbitrary number of pedestrians, scooter drivers, any one of which or two or three might be looking at the car. But you as the autonomous car, in this case, how do you signal to each of them what your intent is? Do you see that any solutions for that problem?
Yeah, that's a really great question. In Ithaca and many places in the U.S., if you come to a stop sign, especially, whether you're a pedestrian and cyclist or a pedestrian in a car or something like that, you typically make eye contact. Sometimes there's a motion that says, okay, you go first or something like that. But there is this second level of communication to communicate intent, which is exactly what you're having in there. In Hanoi, when I was there, there was no, I didn't really see any communication of intent like that. It was just more keeping an eye on what people were doing and just understanding what they were doing, things like that. Because like in the scooters, you can't see their faces, their hands are on there. So it's really hard to communicate intent when you're actually on a scooter. And if you look at those people that I showed in the video when they were walking across the street with all those cars going, I mean, they were just walking, right? You know, and so I think there was basically learned behaviors in those environments that everybody knew. And so that's why, again, when I was first there and my colleague took my hand, you know, she didn't want me to do a behavior that they weren't expecting. And in that case, there would have been an accident or something like that, because I was doing something based on, you know, my behaviors in the US, which does not translate to Hanoi. But I think you bring up a really good point, is that there, you know, a lot of the accidents, but especially when you get to dense scenes, a lot of the potential interactions have challenges that could lead to accidents and things like that. So you'd love to have a second level of communication. You know, if you're in a self-driving car, it's typically pretty easy. I mean, you could do some type of signage or traffic or some type of signal or those types of things, right? Just to be able to communicate those kinds of things, right? But I think when you get
Professor Campbell, if I could just interrupt for a second. I've heard that as a possible solution, but that ignores that there may be more than one pedestrian, bicyclist, or even some sort of a pet or an animal owner and so forth. So you can't just blithely say that. I believe that you just put a signal, a happy face or a sad face on the windscreen. Nobody's going to know who that applies to, and they're just going to assume that. Oftentimes, human nature would be just assume the best possible case for me as a pedestrian, but the bicyclist is going to do the same. Then we have a collision.
Yeah, no, I think you're spot on. I'm not quite sure exactly what the solutions are. I mean, I think, you know, having some type of intersection like the data collections around here, where you're actually communicating, everybody's communicating to a central node. I think that helps, but that helps for lower number of cars and/or, you know, when there's a lot more autonomy in the system and things like that. Again, what's interesting about the Hanoi is that the density is really high, yet there's not a lot of accidents. And again, I think that's just because they have some type of shared behavior that they all trust, right? I'm not quite sure, because that doesn't necessarily.
Can we really trust the statistics? I found that sometimes there's an attempt to make a particular society look better by just ignoring or suppressing actual injuries. And also there's maybe in the case of these slow speed types of interactions, the collisions are not fatal. So they wouldn't necessarily lead to a official report that could be found.
Yeah, I think you're digging into information I don't know a lot about. I don't know what Vietnam reports or those types, you know, things and things like that. I mean, my data and my experience is fairly narrow, right? You know, we had her driving around in a couple hours, but I was just blown away by the fact that there were so many scooters, like I showed in the previous video. But there was, you know, most of the intersections there weren't traffic lights, and so it just sort of, you know, parted the sea. And so there's definitely some behavior there. You know, whether that behavior leads to a higher number or lower number of accidents or something like that, I'm not sure.
Thank you very much for your presentation. It's been phenomenally illuminating to me. Thank you.
Yeah. Other questions?
No, yes.
Thank you for the great presentation. So I'm staying with the condition tracking. Intriguing. So you showed some examples of segmentation, distance segmentation, and tracking of 3 instances.
Yeah.
How about how many of the instances or the objects in the scene are actually segmented by the static class?
Yeah, I should probably show a video of that also. I think, you know, if you take it frame by frame, it's actually much better than I thought it was going to be. And so this right here was, I think it was with Sam too, if I remember correctly, the example that I showed back here. And all we did here was pull out just to show you, you know, some things that were working, some things weren't. So anything close to the car seems like everything was working really quite well. Again, we just ran, you know, SAM2 over the data set just to see how well it worked. Things like that. It was really more when things got occluded that things got more interesting. But then you have to ask the question, well, you know, do you care? Do you care that, you know, I mean, I care about this one that's close to me as opposed to if it gets behind there, maybe I don't care. right? So it could be that, with segmentation, that's good enough. But what we found was that in these dense scenes, once the range got to be a certain level and the occlusions happened, and then we sort of lost track of that.
So also when segmenting a couple of times, then you can do some predictions.
Yeah.
And use those predictions, the rest of the
Absolutely. Yeah.
And another question is related to visual localization. So I'm a little bit intrigued about the use of uncertainty in this context, because my view, so if I have a system and I try to visually localize or associate my view with history, if the association is wrong, then it's very detrimental to the estimation.
Yeah.
So no matter how big the variance is calculated. So
Yeah, no, it's a great question. I mean, I push on my deep learning colleagues to say, it's really great that you have these average errors in tables in your papers, right? But I'm particularly interested in the distribution of errors, not the average errors, because I'm using that information, right? And so in a lot of cars now, they have ways of, there are approaches to overcoming it, like ensembling, right? So you have multiple networks predicting using the same image, or you have the same network with trained on different backgrounds or different data sets or something like that. So you build some type of uncertainty. Sometimes a voting scheme, they're a little smarter than that, but basically you use that information to try to find those outliers, right? But I mean, again, my goal would be to figure out is there a way of actually predicting what that uncertainty is? And there's people that are working on that. There's Bayesian neural networks, and people work on those kinds of things in addition to ensembling. And now we've done a little bit of work with some variational autoencoders, transformers, where we embed latent variables on the inside and we sample from those and things like that. And so we've been trying to explore that a little bit more to try to figure out what that uncertainty is. But what you love to do is you love to be able to predict if you do have an outlier, right? I mean, my motivation has always been GPS and GPS multipath. And so people have studied GPS. If you're in an area with high rises or something like that, then if the signals will bounce off and then come down, and all of a sudden you're like 50 meters away. So it works really well for bigger errors, not as much for smaller errors. But you really want to figure out these bigger errors as you go along. And many times you just have no idea. I mean, that, like the cobblestones, those kind of errors, those were 100-meter errors in visual localization. Because it could look through the entire database, so it just didn't really know. Now you can be a little bit smarter, right? We could have just said, okay, well, we know we're inside of this bubble, right? And I'm just going to look inside of there. So we could have been smarter about that, right? But again, we were particularly interested in using our databases and deep learning to figure out where these outliers were happening and whether we could predict. So again, I don't want to leave you with like visual localization is bad or we don't know how to do visual localization. We were particularly interested in just trying to figure out what those errors would be, whether we could predict them. And I think it's a hard problem. But if there's anything to take away from my talk today is that don't just look at average error, the distribution of errors. I think it's important for everything. Products.
People have questions from the back. Yeah.
So I'm actually a economist, so hearing about the Hanoi dataset is very interesting to me. So I've had one maybe insight and maybe one question. So the insight is from my intuitive driving experience in Vietnam. A lot of time the way you communicate intent is either by like using some like bodily action, like waving your hand to indicate that you are across the street. Even if you are on scooter, obviously you cannot like look at the face, but you can still
hand signal.
show your hand,
Okay.
indicate that you are silent.
Yeah.
And if you are on the car, you use the horn to basically indicate that you are trying to do something.
Right.
And so that's basically a lot of times you have to basically learn their usual behaviors and try to act accordingly.
Yep.
You see a motorbike on the road, it's slowing down. Most of the time it's trying to either do a U-turn or turn left or right.
Yeah.
Even if it's not turning on the indicator, it might be turning. So that's kind of the behavior.
That's good to know.
The second insight is most of the rules are suggestions.
That I knew, that
Yeah.
seemed like to me.
Yeah, so if you are doing something, you either slow down or keep doing that, but you don't do the exact opposite.
Right.
Because that will lead to accident. So if you are crossing the street, you either slow down when there's a car coming, or you stop, or you try to move faster.
Right.
If you back out, the other motorbikes and scooters will hit you.
Yeah,
That's right. Basically.
yeah, because I mean, it was very clear that there was behavior.
Yeah.
Very, very clear there's behaviors and local behaviors that people learn just from driving in that area, right?
Yeah.
My guess is that's the way it is everywhere. You know, my wife grew up in New York City, Queens, and they just drive amazingly fast around there. And again, the rules are meant to be broken there and things like that. So it's kind of close.
Yeah. So the but the questions so you have collected a very large data set in US, and now you are collecting data in Asian countries. Do you see like any emerging common behaviors or like very different behaviors in terms of data set that might indicate some change in terms of methodologies when, for example, visual localization or like autonomous driving, when you try to develop such a system of US and or Asian countries?
Yeah, that's a good question. You know, I mean, when we published Ithaca 365, that was the first data set that my group has been involved in. And again, my colleagues Killian and Brath are much more involved with data sets and what that means and those types of things, right? And so it's this reliance on labeling and all the data. It's hard enough to collect the data, but then to label it correctly, use it, is just an immense effort. I was telling Stephanie earlier today is that we were trying to get some of our labels. We were working with some companies and things like that. We even had somebody do it, but it was really hard, very expensive to be able to do that in terms of getting the data labeled. So I think the reliance on that data is certainly a limiting factor. I mean, as a perception person, it makes sense to me to use some type of auto labeling kind of thing, but it's typically a little bit more taboo in the computer vision community and things like that to be able to do that, right? You want to, if you're going to publish a data set, it should be clean. But what's interesting to me is that if you're hand labeling or even using tools to suggest things, you're going to make some slight mistakes there as well, like that, right? So I'm not sure I have any great insight in terms of the different data sets and things like that. I mean, I think for what we're particularly interested in doing is looking at challenges that we think industry can't solve right now. And so we might train on other people's bigger data sets that have been developed by companies especially, but then use ours for validation. I mean, in my mind, that's the direction we're going. So then we only have to label a little bit of data to test our conditions, and we can publish that as a challenge for other people, things like that. So like that snowy condition or even some of this, if we labeled this data set for just a little bit to do forecasting and with the many scooters and things like that. I mean, that's something that we could help do. So it's a good question. Any other questions?
Fine. Do you have any question online? Feel free to switch on the camera and just speak up if you do. Yep. All right. Thanks a lot. Okay.